Hey everyone, back to a new awesome video, and today we're going to continue with our series about electricity and magnetism. I hope you can see some significant changes on the lighting of the setup and also that you can see me clearer. This is thanks to some new equipment that I've bought. Today we're going to prove Gauss Law, which we introduced on our last video of this series. So if you haven't seen it yet, go watch it now. First, we will prove that if there is no charge enclosed, the flux is going to be zero. After that, we will see what happens when we have a charge enclosed and prove the theorem also for that situation. And then we will generalize it to many charges. So, let's start! Great, so let's start with the proof. First of all, as we said, we're going to consider the case in which there's no flux. Recall from last time, this is the form of Gauss law. Therefore, we're going to have charge over here, and if there is no charge enclosed on this surface, we are going to have this quantity, the flux, to be zero. In here we have our diagram in which we have a positive charge Q and it is opened. We have here an angle, a solid angle, delta omega bigger than zero, and we have this solid angle that goes over here, and in blue over here these are the barriers of our Gaussian surface, the surface we're going to use in Gauss law. So this is the surface. We're going to have two important sides because electric field is not going to be perpendicular to the surface in this part, nor this part, nor that one, nor that one. So we only need to consider the blue surfaces. This is A1 and this is A2. Now we need to do an analysis with electric field and the normal vectors of these surfaces. We know that this n hat vector always points outwards of the surface, so it's going to be, in this case, over here. That is our n hat vector, and in this case it's going to point in the opposite direction, always outwards of the surface we are considering. Now we need to draw our electric field. Over here it's going to be pointing in this direction. We're going to call it E at 1, at surface 1, and it's going to be constant because this is going to be a very small angle, so we're going to approximate it to be constant along this solid angle. And over here we're going to have E2. That's a weird E. Now that we know this, we can easily find what the flux is. We first have this contribution that is going to be A1 times E1, but it's going to be negative because it's pointing in the opposite direction than the n hat vector. And we're going to have a positive contribution over here of A2 times E2. And this is going to be equal to our flux. Our objective is going to be, well, electric flux, to be more exact. Our objective is going to be to show that this quantity is zero, so that Gauss law is true, because we don't have any charge enclosed over here. Our charge is right there. So we want to somehow relate these two quantities, A2 and A1 and E2 and E1. To do so, what we are going to do is define that this is at a distance R1 and that the second surface is at a distance R2. Now, as this is a very small angle, we know that A1 is going to be equal to R1 squared times this solid angle, and A2 is going to be equal to R2 squared times this same solid angle. Therefore, A1 over A2, I'm going to write it over here, let's see, A1 over A2 is going to be equal to this over that, which is R1 squared over R2 squared. Now, we want to do a similar thing for the electric fields. We know, and I'll write it over here, that E1 is going to be equal to KQ over R squared. In that direction, we're going to ignore that it's a vector. And E2 it's going to be equal to KQ over R2 squared. Sorry, that's R1. Therefore, E1 over E2 it's going to be equal to, let's see, we're going to get lots of cancellations over here. KQ over R2 squared. So, what we see is that in this case, K and Q are going to cancel. And we're going to be left with R2 squared over R1 squared. Now we can use this to express these two quantities in terms of the the quantities with subscript 1. We see the flux, the electric flux is going to be equal to minus A1 E1. We're going to leave those the same. And it's going to be plus. Now, we want to express A2 in terms of A1. And to do so, we just solve for it. And we would find it is R2 squared over R1 squared times A1. And now we want to do the same thing for E2. Solving for it in this equation, we see it's R1 squared over R2 squared times sorry, that's not an E1. Now, we can see that all of this cancels, and we are left with minus A1 E1 plus A1 E1, which is indeed 0, as we were expecting it to be. Now we're going to carry out a generalization of what we had before. Now we're going to have our surface a little bit changed, and we're going to make this last A2 have an angle with respect to the surface A1. This angle is going to be theta. Therefore, we have our height from before, it's called S, it's this distance. Now we have the same width, but the surface A2 is now going to depend on that quantity L. A2 prime, our new surface, is going to be L times W. Now, we would like to express this quantity in terms of our old A2, for which we have already proven that there is no flux in this surface. To do so, we would like to relate L with S. And we can see we have a 90-degree triangle over here, and we can express L, which is the hypotenuse, in terms of S as S over cosine theta times W. And we also know that S times W, it's our old A2 surface. So we have A2 prime equals A2 over cosine theta. Now we would like to see what E2 times A2 prime is. Well, times the new n hat. Now, these two vectors are at an angle, and they are specifically at an angle theta. Therefore, their dot product is going to be E2 cosine theta. And you're probably now seeing where this goes. If we substitute our expression for A2 prime, we found over here, we get A2 over cosine theta. And we have some cancellations between cosines, which means that this is going to be equal to E2 A2. Our new flux of this inclined surface is going to be the same one as our old surface. And before, we have proven that for this flux, the total flux is zero, as there is a cancellation with this one. Therefore, we have proven that this is also a situation where Gauss Law works. Great, now we just need to carry one more generalization to prove the situation of Gauss Law for no charge enclosed. We're going to have a surface, a general surface, it can be whatever we want, and we're going to have our charge that is not going to be enclosed. This is a three-dimensional surface that goes around here and goes back. It's kind of a blob a surface of a blob. And we're going to divide this surface in lots of infinitesimal planes for angles d omega. We're going to have it over here, a new plane, we're going to have a new plane over here, also another one over here, another one, and these planes are going to be parallel to the surface of our Gaussian surface. What we're going to see is that each of these planes is going to cancel in pairs with another one. This one will cancel this one. This one will cancel this one, and so again. And if we add up all over this Gaussian surface, what we'll find is that the total contribution for Gauss Law, recall, it is in this form, the total flux over this Gaussian surface is going to be equal to zero because of these cancellations. Great! Now we're ready to start enclosing point charges. We're going to have this point charge Q over here, and we're going to have a fairly general shape that is going to contain it. It's going to enclose it. So at first sight, there's not too much we can do with this, but what we're going to do is to define an inner surface, which is going to be a sphere that encloses this point charge. On our last video, we proved that Gauss Law indeed works when we have a sphere with a point charge on the middle. Now, what we are going to do is to connect these two surfaces. Imagine this wasn't two different surfaces, but they are really connected by different lines, really small with almost no area, so that all of this is a closed surface and the inside is this region over here. In that case, we have proven earlier that for any surface, the total flux is zero. Therefore, we're going to have that the flux coming from the inside of E dot n hat dA, and note that we're going to have an n hat over here. This is going to be n hat in. This is going to be n hat out. And for this computation, when we're considering the whole surface as one, we need to define this n hat out prime which is going to be the n hat of the whole surface. In that case, the one we are considering here is n hat out. And we know that if we add the contribution, as these are integrals, from the outside surface, we're going to get E times n hat out dA equals 0. Now we see that these two vectors are really the opposite of each other. So taking this to the other side and with a negative sign from changing them, we find that the flux in the inner sphere equals the flux on the outer surface. Therefore, by proving that this flux indeed obeys Gauss' law, as we did on our earlier video, we now know that this Gaussian surface with this flux, which is the same one as before, also obeys Gauss' law. Alright, now we're ready to carry out the final step on the generalization and proof of Gauss' law. Many charges. As before, we're going to have some charges inside this fairly general surface. And we know that the total flux from the outer surface is going to be, well, the outer surface is going to be the total electric field times this vector dA. However, we know that this total electric field is no other thing than the sum from E1 plus E2 plus E3 from the contributions of each of these charges. Therefore, this is really no other thing than the same integral from E1 plus E2 plus E3 times n hat out, let's write over here, dA, and those are closed integrals. And by properties of the integrals, we can expand this in three different integrals. And we already know that if we create these auxiliary surfaces, S2, S1, and S3, doing the same process we did earlier by connecting them and with the outer surface, what we can do is to convert each of these integrals around the outer surface into integrals around these inner surfaces. We would have that the flux, electric flux, is the integral over S1 of E1 times n hat 1 dA plus the second one plus the third one. They are really symmetric copies of each other's. And we know, because we found earlier, that these integrals obey Gauss' law. Therefore, we have this is Q1 over epsilon naught plus Q2 over epsilon naught plus Q3 over epsilon naught. And we find that the flux, the electric flux, equals the sum of all of these, which is really the charge enclosed, Q enclosed, over epsilon naught. And this is the statement of Gauss' law, which means we have proven it. Quod erat demonstrandum. What was intended to prove. That is all for today. I hope you understood everything and that it helped you gain more insight about what Gauss' law really means and where it comes from. In future videos, we'll treat some applications of Gauss' law in different situations. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, subscribe to the channel, press the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!